So this chapter is on digital radiography. Okay. This is just some different terms that have kind of evolved over time. We used to call in film density was like the overall blackness of an image. But in digital imaging, we just refer to it as brightness. Okay. Remember, brightness is going to be your window level. And on your phone, remember that because how do you change your brightness on your phone? Okay. So that's going to be your the digital term for your overall degree of image darkening. It's going to be brightness. Okay. Latitude, your latitude and your dynamic range were like your shades of gray. It used to be called latitude with film. Now they use the term dynamic range. So it's the numerical range of each pixel, and it refers to the shades of gray that can be represented on the image. Okay. Film speed, and then now it's called linearity, and then contrast, and now it's contrast resolution. So it's just showing you the difference in verbiage from film to digital. All right, so your digital radiography has 3 elements. They're going to be your capture element, your coupling element, and your collection element. Okay, your capture element is where the X-ray is captured. Okay, so in CR, it's going to be your photostimulable phosphor, your PSP. Okay, in digital, it's going to be your sodium iodide, your cesium iodide, gadolinium, or your amorphous selenium. Okay, so those are the different capture elements that digital uses. Okay, and then your coupling element is going to be what transfers your X-rays generated from your capture element to your collection element. Okay, it could be lens or fiber optic. And then the collection element. Okay, and that's going to be your photodiode, your CCD, which is that charge coupled device. There's your photodiode or your CCD, charge coupled device. Or your TFT. Does anybody remember what TFT stands for? Film transistor. Okay, so the photodiode and the CCD are going to be light sensitive devices that collect the light photons. Your TFT is a charge sensitive device that collects electrons. Okay, so photodiode and CCD, light sensitive, collect light photons, and then your TFT is going to be charge sensitive and collect the electrons, okay, with charge. This diagram on the PowerPoint and this diagram on page 202, 13.1. This is showing you all the different avenues of digital radiography, what each one uses for their capture element, coupling element, collective element. I would know this diagram like through and through. Okay, so know like in CR, what do you use for your capture element? It's your PSP, but what's it made of? herbarium for all that, yep. And then SPR, which we're gonna go over, and then your indirect DR, and then your direct DR. So what capture element pertains to what part of DR, and then the coupling element, the collection element, like how they are made into the image. Some different abbreviations, and now also on the bottom of that figure 13.1, there's all the abbreviations: CCD, charge coupled device, DR, digital radiography, CSI, your CCM iodide. Know all those abbreviations, okay? And then these are gonna be your collection elements for each one: CR, SPR, indirect DR, indirect DR, indirect DR, which is that bottom row in green on that chart, okay? Okay, so your capture, like I said, where the X-ray is captured, it can contain any of these things depending on what we're using, what system it is. Then the coupling element is where the X-ray is generated. The signal is transferred to the collection element. Okay, these are either lens or fiber optic. You can have a contact layer or that amorphous selenium. In direct radiography, it's just the amorphous selenium. And then your collection element, so your photodiode or your CCD or your TFT. Okay, scintillator is the material that exhibits scintillation, which is the property of luminescence, or your light, when excited by ionizing radiation. Okay, it's like a small flash of visible or UV light emitted by fluorescence in a phosphor. And this happens when it's struck by a charged particle or a high energy photon. Okay, so luminescence when excited by ionizing radiation.
This is hot.
She just has it in the slide. So you'll have to refer to the PowerPoint in the book. It didn't really, it talks about the scintillator in the book, but it doesn't really explain what it is, so she added an extra slide so it's like, know what it is. It talks about the scintillation phosphor on page 203. Okay, so back to 202, and she just wanted to explain scintillation, and then we'll go to the scan projection radiology. This was originally developed for CT, and it shows a scan projection of the body in CT. So that figure 13.3 on page 203 is going to be that scan projection. It's kind of like a scout image. Have you ever heard them say that in CT, a scout image? Okay. So your X-ray tube is stationary as the patient travels through the gantry. That's what they call the big CT dome, like the gantry, okay? And this results in a digital image. Okay, so the X-ray tube and the detector do not rotate. They are stationary. And the result is a digital radiograph. The advantage of SPR was collimation to a fan X-ray with associated scatter radiation rejection and improvement. So that picture 13.4 on page 203 shows you it has that collimator in. So it helps with scatter radiation rejection and it improves your image contrast, okay? Because that's the end collimator. Okay, and this does use a scintillation phosphor, which is that recognizes the small flash of light, the luminescence. Okay, they use the sodium iodide or the cesium iodide. The disadvantage to this is patient motion, okay, because they're required to hold still for several seconds. CT has come a long way, and now it's super fast, but back in the day, they used to have to hold still for a few seconds, otherwise we would have motion on the image. All right, so the capture element in CR is your photostimulable phosphor. In DR, it's going to be your cesium iodide, your gadolinium oxysulfide, or your Morpheus selenium. So next is the charged coupled device. And that's going to be in what part, what element? Do you remember what the CTV was in? The collection element. And part of the collection element is a light sensing element. It collects the light photons. Okay, and there's 3 advantages of the CCD. Sensitivity, dynamic range, and size. Okay, so it's a light sensing element, collects light from the scintillator. It's going to lower your exposure time and lower patient dose. 3 advantages are sensitivity, so its ability to detect the light, your dynamic range, so the range of intensity, your shades of gray, and your size. The 2 terms at the top of 204, sensitivity, that is the ability of your CCD to detect and respond to very low levels of visible light. Okay, so that is the sensitivity. And then your dynamic range is the ability of the CCD to respond to a wide range of light intensity, from dim to bright. Okay, so just like in your shades of gray, like the dynamic range, okay, very dim to very bright. So your CCD is going to have a high sensitivity to X-ray exposure and a very wide dynamic range. Okay, so remember, very dim to very bright, but a wide dynamic range. So it can respond to lots of different ranges of light intensity. Okay, an exposure, it's gonna convert light into electronic charge at discrete sites called pixels, photodiodes, or capacitors. And then charge transfer, one of the CCD types is used, CCD or CMS. And then charge to voltage is your signal conversion from analog to digital. So remember that video that we watched that it went through that digitizer and it converted it into all your zeros and ones? Okay, so your analog to digital converter. That last little paragraph, it's your CCD is very small, approximately 1 to 2 centimeters. So the pixel size can be 100 by 100 micrometers, which is really, really small. But the smaller the pixel size, what? Okay, just a quick overview of your CCD. What is it? An analog shift register. It enables the transportation of analog signals through successful stages, your pixels. In an array of photoelectric light sensors, so it's sensing that light. Remember, it's got that wide, what? Dynamic range, okay? Very dim light, very bright light, and comprised of lots of individual signal capture units. So it consists of capacitors and pixels. Your capacitator in digital radiography is like where the image is stored until processing. So like your latent image. Okay. So remember, those were the three characteristics of your CCD: sensitivity, dynamic range, and the size, which is very what? Small or large? Very small. Okay, that's just showing you your CCD chip. And it goes to your pixel, and then your analog to digital converter, and then your data formatter, which gives us our image. Figure 13.6 at the top of 204 is showing us the radiation response of a CCD device. And notice that digital has a linear response. And then your screen film has like that characteristic H&D curve. Okay, so just remember that your digital image receptor has a linear response to radiation exposure, the radiation response. Okay, your CCM iodide, which was also your CSI on your figure 13.1. And your CCD device. This is gonna be indirect digital radiography. It's on the third one in your figure. Okay. Okay, and this uses those tiles, it uses tiled CCDs that receive light from the scintillator. Which allows the use of the X-ray beam. Okay, these are transmitted through fiber optic bundles. Okay, if you refer back to your figure, the coupling element is those fiber optics. And indirect. So, anybody remember the difference between indirect and direct? TR? So your indirect is gonna take your, everybody remembers, your X-rays to light, and then your light is gonna be changed into your electronic signal? No? Okay, so indirect is gonna be X-rays to light. What? What'd you say? Okay, X-rays to light and then light into your electronic signal. Your direct DR is direct from X-ray to electronic signal, so it skips that light phase, okay? So indirect is just a two-step process, direct is a one-step. Okay, so indirect, X-rays to light, light to electronic signal. Direct is X-rays to electronic signal. Okay, indirect, X-rays to light, light to electronic signal. Okay, and your direct is gonna be X-rays to electronic signal. Okay? You're welcome. I wanted to add on the CCM iodide CCD. Sometimes it has issues creating a seamless image. Like there can be breaks in it instead of just a seamless image. The way they fix this is by that interpolation where it fills in the pixel values. But just remember that one of the disadvantages or challenges of the CCM iodide CCD indirect is the creating that seamless image. Okay, now your CCM iodide amorphous silicon. Okay, this has your scintillation light to your collection element. Okay, coming back on your figure. This is going to be indirect DR. Okay, so the collection element in this one is going to be silicon, and it's going to be sandwiched between your TFTs, which are your thin film transistors. Okay, silicon is a semiconductor. So what does that mean when I say semiconductor? It allows what? Some electricity. Okay. your CCM iodide has a high photoelectric capture because the atomic number of CCM and iodide are high. Okay, so it's going to absorb a lot of that photoelectric. So X-ray interaction with your CCM iodide is going to be high because the photoelectric is going to absorb it, which is going to make your patient dose do what? Absorbed. By that, your patient dose is going to go down. Once again, this is indirect DR, so you're going to make X-rays are going to go to what? Light, and then your light is going to go to electronic signal. Okay. That image is on the top of 205. It's just showing the CCM iodide phosphor and X-ray absorption in the scintillator. And this is also the images in the CCM iodide. Does anybody remember what those thin film transistors are? They're like little switches. Okay, that you can like open or close or turn off or on. Each one of those little squares is a pixel in the image. Okay. So the pixel has that switch and it has the storage capacitor which stores the latent image. So each little pixel contains that and stores whatever the information is on that each pixel. Okay. Each pixel is very important because a portion of the pixel face is occupied by the conductors, the capacitors, which store your image, and the TFT, which is the switch. Okay, the percentage of pixel face that is sensitive to X-rays is called fill factor. It's on page 205. Okay, the percentage of the pixel face that is sensitive to X-rays. It's called the fill factor. The fill factor is approximately 80%. Therefore, 20% of the X-ray beam does not contribute to the image. Okay, because your fill factor is that percentage that is sensitive to the X-ray, sensitive to the. So 20% does not contribute to the image. Okay, as pixel size is reduced, spatial resolution is increased. Yes, spatial resolution improves, but that also does what the patient does. Increases it. Okay, so smaller pixels, your fill factor is going to be reduced. But your X-ray intensity must be increased to maintain a good signal strength, which is why your patient dose increases. this is another one that is not in your book, but your detector element is called your DEL. And it's the sensing element of the TFT, which is the switch. Okay, so the smaller the DEL size, the better the spatial resolution. And the greater the fill factor, the better the spatial resolution, but at the expense of completion dose. Okay, spatial resolution in digital is limited to what? What is it based off of? Pixel size. Does anybody remember what it is based off of in film? Spot size. Make a note of that. So DR, spatial resolution, is limited to pixel size, and we cannot image something smaller than the pixel. Can't image something smaller than the size of the pixel. Okay, and the last one is amorphous selenium, which is your direct DR. And direct does what? It takes X-rays into what? Directly from X-ray to your electronic signal. Okay, it skips the light part. Okay, X-rays to electronic signal. Okay, X-ray interacts with this amorphous selenium, producing a charge. There is no scintillation phosphor. Okay, DR does not contain a scintillation phosphor. Okay, so the image forming X-ray beam interacts directly with this amorphous selenium. No scintillation. And it is both the capture element and the coupling element. Okay, so it's both. When you go back to your figure 13.1, it is both your capture element and your coupling element. That's why it says none under your coupling element. Okay, acts as both. So it captures your image. And then your charge is collected by the storage capacitator. Remember, those are in each pixel. That's what stores your image. Okay, and it is stored in the capacitator until it is read by the switch of the TFT. Okay. Okay, it is approximately 200 micrometers thick. Has excellent X-ray absorption. Conversion properties. converting your X-rays into image and spatial resolution, which is high DQE. Does anybody remember what DQE stands for? No, it's the detection quantum efficiency. So it's how well the system converts photons to an image. Okay, that is your DQE. So a high DQE is good or bad? Good. Okay. So how well it converts that photons to image. Okay, X-rays are converted directly to electronic signal, direct. Digital. TFT collects the charge in the matrix of the dells, and spatial resolution and direct PR is fixed. And that's just showing your storage capacitor, your TFT, which is the switch, which reads the image. Those are your collection elements. I couldn't figure out how to move it back to where the collection element, where I talked about collection element, but those are those three. And you'll see the term AMA, like in the AMA of Dells, which is your active matrix array. So that is just a refresher on what AMA stands for. It's your matrix, it contains your pixels, converts your X-ray energy to electronic signal. Each pixel has a TFT, the switch, and capacitor. Okay, so digital radiography, two methods. What are they?
Direct.
Indirect. Okay, indirect does what? How many steps? It's X-rays to light, and then light to electronic, okay? And then your direct is X-rays to
Electronic.
okay? Indirect uses a scintillator, direct does not. Okay, X-rays are converted directly to electronic signal. That's showing you a pixel. And one other thing too, I was gonna, do you guys remember what the pixel pitch was? No. Write this down. Pixel pitch is distance from the center of one pixel to the center of the next. And then your pixel size is your image size divided by your matrix size, your number of pixels. Image size in millimeters, matrix size in pixels. Everybody get pixel pitch, the center of one pixel to the center of the next. Okay. There may or may not be a question on that. Okay, this is showing you two different types of indirect and then direct. So X-rays come in, they're indirect. both have a scintillator, visible light, one uses a CCD or a CMOS, what it called, and the other one uses a photodiode and a TFT. Direct, X-rays come in, charges, TFT. Okay, really know this figure 13.1, it's really useful knowing the different parts of each one. Any questions on 13?
For the quiz, what should we most, is it just like over the entire chapter kind of, or?
Fine.
Yeah.